All right, here's solutions for perfect problem 7 for math 243. It's actually not going to be due May 28th, but whatever. Due sometime in the future. I don't know when. Maybe May 31st. I don't even know if there's 31 days in May. Whatever. It's due later. So what's going on in this problem is we're doing hypothesis testing. But this is a little bit different because the information we have, if you read through this, you won't see anything about means and standard deviations. Instead, you see proportions. We have qualitative data. It turns out you can still do hypothesis testing with qualitative data. And it'll follow very similarly to how we did hypothesis testing when we had quantitative data. Just our pictures will look a little bit different, I guess is the easiest way to summarize it. So let's go through read what we have. I claim that living in the Bay Area affects whether a basketball fan will watch the NBA Finals. Suppose I know that 60% of all basketball fans watch the finals. This 60% right here is very similar to mu naught from our previous section. Right, the population average before we consider whatever the criteria is being tested. This is like mu naught, however, there is no mu in this problem because we don't have averages. We're not talking about quantitative data. We're instead talking about qualitative data. So instead of being mu naught, this is similar to p. We'll use the symbol p naught to represent it. The proportion of the population, of the entire population that watches basketball, before you consider things like whether or not they live in the Bay Area. But in a random sample of 100 Bay Area basketball fans, so this tells me that n equals 100. I guess this tells me that p naught equals 0.6. 65 of them watch the finals. So I know that 65 out of the 100, maybe we'll go over here, 65 out of 100 is what p hat is. Sample proportion. Right, this is similar to x bar from the previous section, the sample average. But now it's not a sample average, it's a sample proportion. Test my claim with 90% confidence. So what that tells us is that alpha is equal to 0.1 or 0.10. And what's the claim? I claim that living in the Bay Area affects. Affects will be a key word here. I don't say that if you live in the Bay, you're more likely to watch the NBA Finals, nor do I say that if you live in the Bay, you're less likely to watch the NBA Finals. Say you're differently likely. It affects. So what that tells me is that I'm going to end up with a two-tailed test. Maybe I underline that. That's a key word. Affects. All right. Hypothesis testing. First with the classical method. State the null and alternative hypotheses. The null hypothesis, well, the alternative hypothesis is always the claim. In this case, I claim that living in the Bay Area affects whether a basketball. Okay, so when we were dealing with this before, my alternative hypothesis would always be that mu and then either greater than, less than, or does not equal mu naught. But we don't have a mu and a mu naught here because we're talking about proportions. So instead we have a p and a p naught. So both my null and my alternative hypothesis are going to compare p and p naught. My alternative hypothesis is my claim. And my claim is that P, the proportion of basketball fans that live in the Bay Area, the population for everybody that lives in the Bay Area, does not equal 0.60 or 0.6. Whereas my null hypothesis is that P equals 0.6. So the point that I want to make is that this is very similar to our null and alternative hypotheses before, except there it was mu equals mu naught, and mu less than, greater than, or does not equals mu naught. Now it's p equals p naught, and p less than, greater than, does not equal p naught. Because I put does not equals there, I have a two-tailed test. Null alternative hypothesis. State/justify the shape, center, and spread. Later on I'm going to be drawing pictures. If I want to draw a picture, I should probably give the reader some information about the picture, specifically the shape of the picture, the center of the picture, and the spread of that picture. So the shape better be approximately normal, because that's all we know how to study in this class. We have a criteria, kind of comes from our central limit theorem, that the shape of a proportion will be approximately normal anytime. We used to say n times p times 1 minus p had to be greater than or equal to 10. Problem is we don't know p in this case. But what we do is we start out by assuming our null hypothesis is true. And our null hypothesis is that p equals 0.6. So you can kind of put p naughts in there if you want. Or you can leave it as P, I don't really care. But we're going to assume that P equals P naught. So it doesn't matter what you use, they're the same thing. And if you check this out, N is 100, 100 times 0.6 times 1 minus 0.6 is equal to 24, which sure enough is greater than or equal to 10. Center. Center is given by P naught. I'm just going to write P naught equals 0.6. The spread. I'm not going to, well, the spread, we used to use the formula P times 1 minus P divided by N. Square root of that gives me my spread. We don't know P. We can use P naught instead, since our null hypothesis is that P just equals P naught. So my spread is the square root of 0.6 times 1 minus 0.6 divided by 100. Whatever that number is equal to is what my spread is. Okay, so now it wants me to sketch a distribution showing the critical value or values, alpha, and the test statistic. So here's my picture. It's pretty good. Approximately normal distribution. This is going to be classical hypothesis testing here. I'm going to draw this distribution. I'm going to draw it approximately normal because that's what I said the shape is. And I'm going to put the center at 0.6. But then I'm going to remember that whenever I'm doing hypothesis testing, all the data is given to me in terms of z-scores. So I'll put a 0 below that. And now what I got to do is I got to figure out where my rejection regions are. I got to find my critical values, which are the boundary points for my rejection region. Put it over here, or do you put it over here? Answer is both. I got a two-tailed test, so I'm going to have a rejection region over here on this side, and I'm going to have a rejection region over here on this side. Whoops. Good enough. So how do I figure out those values? Well, I know that the total area of my rejection region is 0.1, and I split it in half, so that means this side is 0.05, and this side is 0.05. So what I got to do is I got to figure out the critical value. I got to figure out what z-scores correspond with the endpoints of these critical values. The good news here is since I'm talking about proportions, I have a z distribution. When I have a z distribution, I can just use the inverse norm function on my calculator. So if you hit distribution and then go to inverse norm, then all I got to do is tell it the area below the point in question. So if I'm trying to figure out this one right here, I'd say 0.05 is above it, so 0.95 is below it. And I want a z-score, so I'm going to put in comma 0, comma 1. That gives me 1.645, which is this critical value. And if this critical value is 1.645, this one must be negative 1.645 due to the symmetry of my distribution. If you don't believe me, you could do inverse norm again, except this time instead of 0.95 is the area below, put in 0.05. Now I'm trying to find this point. The area below this is 0.05. Hit enter, and sure enough, you get negative 1.645. So part B-C said sketch a distribution showing the critical values, that's this guy and this guy, alpha, that's this guy and this guy, and then the test statistic. To figure out the test statistic, I have to run my hypothesis test. To do that, you hit stat, go over to tests, and then one prop z test. One prop because we're talking about proportions here, and then z test because proportions always follow my z distribution. Hit enter, and it'll ask you for some stuff. It'll ask you what P naught is equal to. P naught's equal to 0.6. I have that written all over the place. I have it written down here. I have it written up here. X. X is the number of people in my sample that have the criteria in question. In this case, X is 65. N is the number of people in my sample, which is 100. It's really tempting to put 0.65 up here. It doesn't want that for X. It wants the number of people. It'll figure out P hat. You don't tell it P hat. It calculates that for you. And then it says, what's your claim? What's your alternative hypothesis? Well, my alternative hypothesis is that P does not equal P naught. P does not equal P naught. It's this first one here. I'll go to calculate, and it'll give me some information. Specifically, it tells me that the z-score is 1.02. Somewhere over here, 1.02. Right, it's less than 1.645. My test statistic, maybe let me write that a little bit better. all about test statistic equals, what was it, 1.02? My test statistic is not in the rejection region. Draw your conclusion? Sure. Because test statistic is not in a rejection region, there is not sufficient evidence to reject the null hypothesis. The null hypothesis is on trial. I'm not saying it's innocent, I'm just saying it's not guilty. I don't have enough evidence to reject this thing. I'm not saying it's right. I'm not saying that the proportion of people in the Bay Area that watch the finals is 60%. I'm not saying that when you live in the Bay Area that does not change whether or not you watch the NBA finals. I'm not saying that. I'm just saying there's not enough evidence to conclude that living in the Bay Area affects whether you'll watch the finals or not. Not enough evidence. Because the test statistic is not in the rejection region, there is not sufficient evidence to reject the null hypothesis. The end of part 1. Fortunately, part 2 is a little bit easier. Part 2 is same thing, it's hypothesis testing, except now I'm going to use the p-value method instead of the classical method. The nice news is that the null and alternative hypotheses are the exact same. I don't have to rewrite these. And the shape, center, and the spread are the exact same. I don't have to rewrite all this. So the first thing that I have to do is draw a picture. Again, because my shape is approximately normal, I'll draw something that's approximately normal. I'll put 0.6 in the middle, and then I'll realize that that corresponds with the z-score of 0. And then, unlike in the classical picture, I'm going to sketch a distribution showing only the test statistic and the p-value. So I don't need to set up rejection regions. I don't have to do that inverse norm thing that I did before. All I got to do is find the test statistic, that 1.02, sketch this, shade this area in here, and then because we have a two-tailed test, my p-value is going to be on both sides of the distribution. So what I'm saying is 1.02 is here, I'm going to put negative 1.02 here and shade in this side also. My p-value will be the total of those two areas. So this area and this area together. This is my p-value. And my p-value is equal to point, given to me in the calculator here, 0.307 maybe. 307, why not? So this is my test statistic. This is the negative of my test statistic. And then that shaded region is my p-value. But it turns out that this picture is sufficient to draw your conclusion. We'll have the same conclusion we had up here. There's not going to be enough evidence to reject the null hypothesis, but my reasoning on why is now different. Now I'm going to say because my p-value is greater than alpha. Remember from before that alpha is equal to 0.1. My p-value is 0.3. 0.3 is greater than 0.1. Because my p-value is greater than alpha, there is not sufficient evidence, blah, blah, blah. Spelled sufficient, different. I don't know which one's right. Right, messy, and then nobody can tell. Because the p-value is greater than alpha, there is not sufficient evidence to reject the null hypothesis. Same conclusion, just for a different reason. That's it. That's the end. Classical picture, p-value picture. Maybe I'll label it. Well, it says p-value over here. I'm going to call that good enough. I think I'm going to end this right here.